Hi, everyone. We are going to be continuing our conversation on solid earth circulation and plate tectonics. So, in previous lectures, we were discussing the structure of the earth and all the layers. We are going to expand on that today by getting into the mineral and material composition of the earth, and then also diving into some generalized rock classification, um, the key minerals of the earth, and then ending with the rock cycle. And then in the next lecture, we will continue our conversation with discussing the theory of plate tectonics. So, in the last few lectures, we were discussing again the different layers and composition of the Earth, where we were talking about the crust at the surface, then that is underlaid by the mantle. Under that, we have the liquid outer core and then the solid inner core. So, what is the composition and the chemical composition of the Earth in all these different layers? So, if we look at the Earth as a whole, so the whole aggregate of all of those layers together, what is that chemical composition? We have that broken down here on the left, where we can see that iron dominates the whole Earth's composition here with 35%. The next runner up is oxygen with 30% of a composition there. Then we have silicon at 15%, magnesium at 13%, and then we start getting into the single digits and below with some other key elements there. Okay, so if we're not talking about the Earth as a whole, right, and we look at some specific layers, we can then divide this out, right? So not shown here, the breakdown, but if you remember from last week's lecture, we know that our core, both our inner and our outer core, are dominated by iron. So our core has 80% iron, and then we have 5% nickel, and so on in that, right? So most of that iron that we have in our whole Earth composition is in the core, both the liquid outer core and then the solid inner core are both dominated by iron. And remember the conductive increase the magnetic field. Okay, so now let's talk about the Earth's crust and then the mantle. Well, the Earth's crust has a quite different composition here. We The iron is not dominating anymore, right? Because it is in the core of the Earth. So instead, in our Earth's crust, oxygen dominates our composition with 46%. Then we have silicon at 28%. So here we're well over 50% here with just those two elements alone. We have then all our other elements in those single digit numbers and percentages and below, such as aluminum, iron, magnesium, calcium, potassium, sodium, and then everything else is less than 1%. Okay, so how is the mantle different from our Earth's crust? Well, it is actually quite similar. So we have also oxygen leading the way in our composition of our mantle, right? That layer below our crust at 44%, pretty similar to our crustal composition of 46. Second place, we have silicon, again, at 21.5%, so in the 20% range, so very similar. Um, the elements with lower concentrations than these two, that's where we start to see a difference. So in our mantle, we have then more magnesium, and another 22%. So that's a lot of magnesium there in our mantle. Finally, in our single digit numbers, we have iron, aluminum, calcium, and then we have some sodium and potassium there at less than a percentage point combined. So putting this all together, what's important to know, right? The Earth as an aggregate, if we think about that composition, we have iron, oxygen, silicon, and then magnesium. And those four elements alone account for 93% of the Earth's chemical composition when we're talking about the whole thing as a total, right? Not breaking that down into those components. Okay, so now thinking about the Earth's crust. Um, So what do we need to know here? Now we know the composition. Well, if we want to think about the Earth's crust, we think of rocks, right? And rocks are composed of minerals. Here is just a figure showing a completely non-extensive or complete list of all different minerals that we have on our Earth. So rocks are composed of minerals. Minerals are defined as naturally occurring inorganic solids of definite crystal structure and chemical composition. So here on the left, we have a comparison of the compositions of our whole Earth as an aggregate altogether versus just the Earth's crust, right? So the Earth's crust is made up of rocks, which is made up of minerals. And minerals, again, are naturally occurring inorganic solids of a definite crystal structure and chemical composition. And 90% of the Earth's crust is made of silicate minerals. And this makes quite a bit of sense, right? So silicate is a combination of silicon and oxygen, right? With 46% of our crust being oxygen and 28% being silicon, it has to be this way. It makes sense that 90% of the minerals on the Earth's crust are the silicate type of minerals. And because of this, because they make up our rocks, the basic silicate minerals are called rock forming minerals. That's like the group of minerals we call rock forming minerals are these silicate minerals. And then quickly, just again to contrast our mineral definition that we have here, which is important to know. A rock, just a simple rock, is defined as a bulk solid geologic material that is relatively homogeneous and at a large enough scale. So a rock can be composed of many things in many different types, but a mineral is more specific in that it must be inorganic, so non-biologic, solid, with a definite crystal structure and a known chemical composition that does not change or changes in a known fashion, but has to have a definite chemical composition. Okay, so if 90% of our crust is silicate minerals, what are the other 10%? So the other 10% of minerals are dominantly, first we have sulfides, which is a binary compound of sulfur. An example of this is pyrite or fool's gold, pictured here. We also have carbonates. So carbonate has a carbon and an oxygen atom in there. The examples of these are calcite or malachite, which is my favorite rock, pictured here because it's just a beautiful green color. Okay, after that, we also have oxides. So corundum is a type of a ruby. So corundum is a rock-forming mineral with an aluminum oxide. So it's Al2O3. And rubies are just a red variety of this because they contain chromium within them. So it's aluminum oxide. Sapphires are also corundums. So a sapphire and a ruby are the same thing, basically. They just have these other tiny trace elements that change the color of these different crystals, but the actual mineral itself is the same. They're both corundums. And then finally, we also have our native elements, such as our gold, our silver, and our copper. So that makes up the other 10%. So right? So this is just the 10%, and the rest are those silicate minerals. And so basically, with 90% composition, Earth's mantle and its crust are made up of these silicate minerals. Silicate minerals, they are a large and very important group of rock-forming minerals, and they're all built from the silicate groups. So the tetrahedron of silicon and oxygen that make up this 90% of the Earth's crust, which is also a giant leader in the composition and very important for the mantle as well. The silica tetrahedron is the basic building block of all silicate minerals. So the silicate tetrahedron um, is the bond form or the crystalline form of our silicon, one silicon, and four oxygen atoms. So they are bound together in a tetrahedron, which is a three-sided pyramid structure. So here in the center of our diagram on the right, we can see in blue our silica and or silicon atom. And then we have in these red, we have our oxygen atoms that are linked to, and then how this silicate tetrahedron is linked together with other ones, that different configuration of how they are linked creates our different forms of our silicate structures, and then all of the different rocks and or all of the different minerals that we know from there. So again, our silicate minerals is this giant class that has SiO4. So one silica and four oxygen atoms that are bound together in this tetrahedron. So this three-sided pyramid. And then how all of these different pyramids are put together and linked in the geometry of those connections gives us so many different forms of our silicate structures and our different types of minerals there. So now I'm going to go over some of these different structures and then talk about what is the mineral and show you an example of that. Okay, so our silicate structures. So the most basic kind here we have is our olivine group, where we just have an independent or an isolated tetrahedron. So they're not bound to anything else, not bound to one another. Instead, they are connected by an external um, atom of either magnesium or iron. And that will create our chemical symbol of Mg2SiO4 or the other. And that is our olivine, which is shown here in green. So we then we have our pyroxene group, where we have a single chain. So all of our different tetrahedra are linked together in a chain. And then we have our amphibial group, which has this double chain. So just two of those chains stacked onto one another. So our olivine metals of iron or magnesium, that is located between our tetrahedra. So here is a diagram showing in red our oxygen, in pink our silicon, and then all those triangles and shaded in pink are our silicon tetrahedron that we just showed before. But they're not really linked directly up to each other, right? We can actually see all these different blue dots, which represent where we will either have our magnesium or our iron atoms. So instead of them touching each other, they are linking together with this magnesium or this iron that's kind of injected in there to create our olivine. Complexity after that is our chain silicates, again, our pyroxene. So these, to create the chain, we have one shared bond between our tetrahedron. So here we can see our first one, and then we just connect our second chain. See how we are sharing and connecting right onto that atom that links them. So that one's shared. Oh, we have another shared bond, creating our chain as we have each of our tetrahedras linking together. So an example of this is our pyroxene or dioxide crystals. This is a picture of one that was taken from, or a sample that was collected in Afghanistan. So chain silicates or pyroxenes are the most significant and abundant group of rock forming ferromagnetism silicates, which is found in almost every variety of igneous or like molten lava rocks. Ferromagnetism is important because, as we were speaking about in our last lecture, the Earth has a magnetic field. So, ferromagnetism means the ability of the rock, it enables the rock to capture that magnetism or react to a magnetic field that is exerted upon that rock because we have all of this iron in it, which is conductive and can align with that magnetic field. So that makes it a very important and abundant group for our to form ferromagnetic rocks. Okay, so whenever we have, right, we have this chain of silicates. Whenever we connect another chain to it right at the bottom, it will create our double chain silicates or our amphiboles. So here's our first chain. Right here, we connect our second chain, and that just shows us here that we have now two shared bonds between our tetrahedra and our metal form of our SiO3. An example you may be familiar with of our double chain silicate is asbestos, which is shown here on the left. That is a common example of a double chain silicate. But our silicate structures do not end here. The next class we have is micas, which will form the silicate sheets, such as biolite or muscovite. Mica is a group of complex hydrous potassium aluminum silicate minerals. And important feature of these is that they can be split into very thin, flexible sheets. So they have all these very thin layers that you can easily break apart and see. Different types of micas are used for insulation, in cosmetics, in paints, for example, and there's a lot of other uses for them. Next up brings us to our feldspar, and then our quartz. So feldspar is an aluminosilicate. So there is aluminum in here in the silicate, and feldspar in particular makes up 60% of the Earth's crust. Is found in all different rock types, and it has potassium, sodium, and calcium in it. It's the most abundant mineral group, and feldspar is used in so many industries and applications, such as in glass making, ceramics, and other industries. Feldspar is also a major part of a rock like granite. There's a lot of feldspar in granite. Okay, finally on the bottom here, we have quartz, which is just our SiO2. So that is only our tetrahedra here. Um, we don't have the addition of any other elements in our quartz. So quartz, it's joined together just as our tetrahedrons. So again, our three-sided pyramids, when they're all stacked together and compact into a crystal structure. So there are a crystalline mineral that is composed of silica. It's a very significant component of many different rocks. Again, the chemical composition, SiO2 or SiO4, with an oxygen shared between two tetrahedra. So it's the natural form of silicon dioxide, and it is linked to the cooling and the solidification of magma. So just a better look at our silicate structures. So here is a diagram showing our sheet micas, our sheet silicates, which are our mica. So instead of that double chain, here we have a triple chain, and it continues onward with three shared bonds between tetrahedra. Again, examples are biotite, muscovite. Okay, so if we look at all of our rock forming minerals, I have a lot of them that we just discussed here, and here is their chemical formulas. What we can see is that is common between all of them. I have highlighted here in yellow where we can see that it is our silicon and our oxygen, right, which is representing over 70% of our Earth's crust composition. So again, our silicate minerals are our most common um, type of rock forming mineral in the Earth's crust and also within the mantle as well. Okay, so now that we talked a little bit about what is a rock and then what is a mineral and what minerals are all important for the Earth's crust composition and our mantle composition, we can now start thinking about rocks in the general classification of them. So, how are these rocks forming? Where do they come from? Where are these different chemicals coming from to put them together? And then, how are we classifying them on the surface? So here on the left, I have a thin section that you can see all the different um, crystal facies of a rock. Um, so again, rocks are composed of minerals. Rocks are important because they actually record the conditions where they form in the earth. And we can use rocks to reconstruct the history of the Earth system. So rocks, again, are composed of minerals, and they can be broken into three broad groups that serve as our main categories for rock classification. These three groups are igneous, metamorphic, and sedimentary. So geologists recognize that there are these three major types of rocks, and we will go into each one specifically and how they form, and then the relationship between them all when we discuss the rock cycle. So, first, igneous rocks. Igneous rocks form from the cooling of magma, which is liquid rock. So, think of Dante's Inferno. They are forming from the cooling of magma, which again is molten rock whenever it is beneath the surface. Once magma reaches the surface of the earth, then that is called then lava. So igneous rocks forming from that cooling of that magma. So liquid molten rock cools and solidifies. Now it's called an igneous rock once it forms and cools. So there are two types of, or two subclassifications of igneous rocks, really. Um, so first are intrusive igneous rocks, and these are the ones that are solidifying below the Earth's surface. And because they are below the Earth's surface, they're not exposed to the atmosphere and all the conditions, so they are allowed to cool more slowly than if they were ejected onto the surface. A very common example of an intrusive igneous rock is granite. So that is very well known. And here at the bottom, I have three pictures of different igneous rocks with granite emphasized here on the right. So if instead of a igneous rock cooling below the Earth's surface, if instead it is erupted through a volcano or a ridge and it is reaches the Earth as lava, then that lava cools. That is called an extrusive igneous rock. So because this lava now has reached the Earth's surface, it's exposed to the atmosphere, it can cool a lot more quickly. So extrusive igneous rocks cool rapidly as magma erupts at or very near the Earth's surface. And then we can then, of these extrusive igneous rocks, so here you can see in the background we have a volcano and we have some lava shown. But so we have our extrusive igneous rocks that are formed from this lava or this magma. We can then classify them into two subgroups based on their composition. So igneous rocks that are have a low silica composition um, are called mafic rocks. And then igneous rocks with a, oh, sorry, low silica and high magnesium or iron composition are called mafic rocks. And then if they have a high silica on the other hand, and then a low magnesium or iron composition, they're called felsic rocks. So we have a felsic rock on the left here that you can see some characteristics of felsic rocks that are high in silica and low in magnesium and iron are that they're typically light in color. They are usually have a higher density as well, but you can really tell just visually if we're only looking at a picture that they're typically light in color. On the other hand, right, we have our mafic rocks that are low in silica and very high in magnesium and iron, and these are typically very dark rocks. So here we have a photo showing a lava flow that then cooled. We can see this lava that flowed right through this speed limit sign across the road in Hawaii. So the lava, once it cools, this is a mafic rock, and in particular, this is a basaltic rock. Igneous rocks. Um, They're produced whenever we have volcanic eruptions, such as the May 1980 Mount St. Helens eruption. So, if we have more silicon and oxygen, we have more power ejected from these volcanoes. Um, I am actually currently at a conference, and I was talking to a colleague who's from Anchorage, and right now they have a volcano warning. So one of the volcanoes in the Aleutian Islands is apparently going to erupt in the next maybe few weeks. So there's an active volcano warning, and apparently at schools there kids have volcano preparedness and volcano warning things, and everyone was told to, have water and, um, masks and goggles for the ash that is expected to rain down on Anchorage. The last volcanic eruption in Anchorage, apparently, with all the ash that was ejected in this pyroclastic cloud, which you can see here in this photo. You see all that smoke coming from that volcano. That's called the pyroclastic cloud that has just this vaporized molten everything that's ejected from this volcano into the air, falls down as ash. That only grounded the airport in Anchorage for 20 hours last time there was an eruption, which is pretty interesting. And I think it's also probably pretty good for the soils to have that ash. But yeah, thought that was interesting. And here is a photo here showing a 1984 Mauna Loa eruption. So in these eruptions in Mauna Loa, there is less silicon and oxygen there, so less silicon. And that means that the lava that's produced is less viscous and therefore less explosive. So here you can see that it is looks quite liquidy, but again, there's not that big pyroclastic cloud that's driving the eruption. If you really look closely in this photo, in the bottom left of it, you can see like kind of a white dot, and that's a person right there. If you see a lot of the eruptions in Hawaii specifically, you'll see scientists sometimes being quite close to the eruption. Whereas whenever Mount Helens erupted, it blew half the top of the volcano off. And now there's a giant crater on the top because of just that explosive power. So, what is cool about these very, very hot rocks? So, the chemistry, the texture, the structure of igneous rocks will tell you what's happening inside of the earth. Lab experiments can recreate the pressures and temperature conditions in which they form. And you can basically, with some different types of machines, you can try to recreate the conditions to create this molten lava in the lab. These lab experiments can especially tell you about the trace element chemistry of all of these different lists of these trace elements. Igneous rocks are also chemically complex. The composition of magma evolves as minerals grow from that magma. Magma chemistry is basically a moving target through time. So in this photo here, we can see the transition between on the right hand side, we have ultramafic on the top, and then we have felsic on the bottom. On the left hand side, we have this thermometer indicating our different pressures. That's also indicated in this red here. So we can see our discontinuous series, residual phases, which are the last to crystallization, so require a more slow cooling of that lava versus our very quick cooling of that lava. And we can see just how all of these different silicate bonds are created in these different conditions. Feel free to pause to look at that in a little bit more detail. Okay, right. So if we have our igneous rocks, right? So just a quick recap, they are forming by the cooling of magma, either whenever it is intrusive, so that it is ejected in the subsurface, so it can cool quite slowly. Slow cooling means that the crystals are allowed to grow larger as it cools. If instead that lava is cooling very quickly because it is extrusive and it is ejected onto the surface, right, where it's in contact with the atmosphere, no insulation is just cooling really, really quick. Those crystals within it do not have time to grow. They are just quickly, quickly cooling. So that's why you will see a lot of mining for, say, precious gemstones in the subsurface. You don't typically just find them rolling around on the top of the ground, um, that are coming right out of a volcano, but they cool slowly in the subsurface. Okay, so that brings us to our next type of rock, which is a sedimentary rock, or our next rock classification. Sedimentary rocks are rocks that are exposed on the surface so sedimentary rocks is the category we're talking about now. Rocks are exposed when they are exposed at the surface. They are exposed to atmospheric and hydrosphere, biosphere, weather. All these things and all these exposures make them become a sediment. So sediments or broken up parts, pieces of rocks, are then transported to low spots in topography or basins where they can then collect, and then they'll undergo something called lithification, and then they become a sedimentary rock. Don't worry, we'll go through this all in a little bit more detail. Um, Example of sedimentary rocks. Has anyone been to the Grand Canyon or see the Grand Canyon? You can see all these beautiful, beautiful layers of all these different colors of rocks. The Grand Canyon is one of the best examples in the world of sedimentary rocks, because of that natural carving through all of this rock, so you can just exposes all these layers over such a vast area. So classic sediments are produced from the normal weathering of any rock, um, producing something such as a conglomerate, which is a rock with a bunch of different larger chunks of different rocks that are all stuck together. A sandstone, which is produced from sand-sized grains put together, siltstone, which has finer grains than sand, and then mudstone, which has even finer um, individual grains, the finest of individual grains that are cemented together to create that rock. They can um, be produced by chemical or biochemical sediments. Um, they are also as evaporites that we talked about earlier in our oceanic circulation section, where I showed you some photos of some halite and some gypsum deposits. And sedimentary rocks are also include limestones. So here are some photos. So here we have a calcium carbonate, which is a type of a chemical and a biochemical sediment. So carbonate, calcium carbonate, is typically produced in the ocean whenever all of the different types of organisms that have shells lose their shells. These shells fall to the ground. They get compacted over time, all these broken up pieces of shells, and then they get cemented together, and then they are forming a rock that we call limestone or calcium carbonate. Here's some more examples of calcium carbonate. Here's a photo of some coarse gravel and sand that has been deposited by a river. Here's a little brush that is showing you just the scale. Sandstone here, which was deposited by running water over time. And here we can see these beautiful layers. Here are some photos of sandstone that have been deposited by the wind instead of water. On the left here is a beautiful slot canyon, where you can see similar types of different sand sediments pasted together. So there aren't these drastic changes in our composition or the size of these grains. But instead, they are all these very fine sands that have been blown together. So it's very uniform here, but it still has all of those layers. And again, water carving through these over time has revealed all these layers for us. Here's another photo on the right of a sandstone with a person for scale. And here you can see these large bedding planes. So these linear features or these lines that you can see on here. So that's kind of revealing those same planes where all those different sediment layers were deposited onto one another. Then we have siltstone. So we have even finer grains of sediments deposited. Here, the siltstone was deposited by water. And finally, we have mudstone. So if you grind that sediment up even finer, the most fine you can, and then you get that wet, it will create a mud. So here's a mudstone that was deposited by multiple processes, such as water, sand, and soil over time that developed these mudstone layers. One thing that you can see here is that those layers are not as linear as the previous ones. Sedimentary rocks are super important because they are how we understand Earth's surface environment in the past. So, the chemical and the physical characteristics of sedimentary rocks give us important clues about past climate, temperatures, and the environment over time. So, we can use these layers and we can then think about what did it take for them to be deposited? Where did they come from? How far did they travel? Did they come from the top of a mountain down into a valley? Was it deposited by wind? What even ground up that rock in the first place for it to be transported by the wind? How strong were the winds in order to blow the particle of this size? What does that tell us about the different weather patterns in the area? Then we can again pull out our dating tools like our carbon dating, our radiocarbon dating, or other types of elemental dating techniques. We can date those different layers, and then we can, piece together a history of an area over time. We can also see how long did it take for all of these layers to form, basically giving us a beautiful history into the past and a look into the past, which again brings us into our idea of our unconformity, which is a gap in the geologic record, right? So if our sedimentary rocks are a great look into the past, right? If there was an event, a erosive event, or that rock was removed for some reason, then we lose that geologic history and that geologic information. The removal of this rock, these rock layers that represent a period of time, is called an unconformity. So again, representing periods of non-deposition, right? So nothing was deposited. That's an example that could happen as well. Or erosion. So things were deposited, then they were removed, and we can't fill in that gap any longer. So here is landform in Scotland. So here we have some Devonian terrestrial rocks. Here we have our Silurian marine rocks. And here, this line here, it represents about 65 million years of missing time in the geologic record, which is again an unconformity. Okay, so this brings us to our final and our third and final rock category, which is our metamorphic rocks. So to create a metamorphic rock, all you have to do is you take a rock, any rock that we've talked about at this point, any type of rock you can find, pick one up. Okay, then you can start heating it up. Maybe you bury it and you bury it deeper and deeper and deeper. And as you get deeper, you're gonna get hotter. Um, so bury it maybe, squeeze it, shear it, deform it while it's hot, it's under pressure. Do anything you want to it, but do not completely melt that rock. Just get it really hot under some high pressures, move it around, whatever you gotta do, but don't melt it. Because again, if you melt that rock, then it becomes an igneous rock, right? Because that's the created by that molten or that liquid rock. So metamorphic, create that rock at the surface or wherever you're creating it, do whatever you want to it, heat it up, bury it, squeeze it, don't melt it, and then you have a metamorphic rock. Here are some examples of common metamorphic rocks. So we have slate up in the left-hand corner. We have some gneiss here with a penny for scale. And we have some schist here in the bottom with a paper clip for scale. Here is a giant example of schist in New Hampshire. You can see some people up at the top of this rock for scale. And you can also see some of these really cool folds that are happening within this rock layer. Metamorphic rocks are very important because, right, they have undergone a lot of things. They've undergone these high temperatures and pressures. So they are very telling because while they're undergoing those things, they are recording the temperatures and the pressures in which that they experienced. So they recorded those conditions of that rock. So we can use that rock to see, okay, well, what happened to it? Where was it? How long was it under the ground? How deep was it? What all happened to it? We can then also use all this information to back out some transit times. So how long did it take from it being exposed at the surface? It got buried at some point. It underwent, some very high temperatures, pressures, and then it eventually got back to the surface because we're looking at it right now at the surface of the Earth. So how long did that take? We can back that out. And also importantly, we can back out these stress conditions in the Earth's interior. So did that rock get compressed? Did it get stretched? Did it get folded about? What was happening to it? How did it all get moved around? And we can use all of this at the surface to understand, okay, what is going on underneath our surface? What's going on in our mantle? And in that, kind of transition zone before that rock would completely melt. Okay, so now that we have our three major rock types, we can talk about the rock cycle, which is the recycling of the lithosphere. So, how are rocks created? How are they destroyed? What happens in between? So, all rocks that are in our lithosphere, which create, again, remember our continental plates, so including our crust and just that uppermost part of the mantle, our lithosphere, all rocks there in the lithosphere ultimately derive from igneous rocks. So rock is born and it is an igneous rock because it came from magma. So some of these are, say, born when they're extruded volcanically, um, maybe at a mid-ocean ridge in the middle of the ocean. Then that rock is going to die ultimately when it's subjected and incorporated into the ionosphere, and melted, and it goes back to the mantle as it's melted down after it's subducted, not subjected. Sorry, that's a typo there. So once it's subducted, and then that, right, so it's subjected underneath a plate, it gets buried so deep into the underneath the earth, into the ionosphere, where it completely melts. So this cycle of being extruded, so born and then dying, basically, on average over the entire earth takes about 80 million years. So extruded, subducted, on average 80 million years. But that is not representative of every rock on Earth. That is just a very cursory average value. This lifetime can vary. For example, the oldest oceanic crust, so in our oceans, is about 200 million years old, a little over that. However, our continental rocks are much, much older on average. The oldest continental rock is nearly 4 billion years old. The oldest of the old rocks are located in cratons. So, craton is an old, previously active, but now tectonically dormant region that is located in the center of a continent. So it's being protected by all of the going onings of our plate tectonic motion, of our subduction and our creation and our destroyal. But it's in the middle of our continents. That's where we have our oldest rocks that date back nearly 4 billion years. Here is a figure showing you some of these cratons and where they're located, specifically the ages of the components of the North American continent, which reveal that the continent has grown by the amalgamation of very old cratons, followed by accretion of younger material onto the periphery of that craton during plate collisions. So we start with this basically enucleation point of our old cratons, and then material is being added onto that over time. So in this figure, we have the oldest continental crust in billions of years in blue. That's over 2.5 billion years old in blue, up through the middle of the northern United States, and then all through the center of Canada, really. We then have our colors from our other crayons that have added on to that. And then we have our youngest crust here elsewhere. Okay, so we talked about the birth and the death in general of rock. But what happens during its lifetime? Well, during its lifetime, rocks are weathered and eroded. So once formed, these igneous rocks are subjected to a variety of processes that will alter their chemical composition. They can also weaken their structural integrity, which will cause their disintegration or dissolution, so dissolving of that rock within a fluid of that original rock. So that rock is going to be breaking down over time. Weathering is defined as the physical, biological, and chemical process of breaking down a rock into small particles, and each of these small particles is called a sediment. And these sediments can also be dissolved, broken down, and put into a dissolved material. So there are multiple types of weathering, right? So physical weathering involves processes such as uplift. So when rocks are uplifted from underneath the earth, right? Or underneath, not underneath the earth, underneath or deep in the crust, as they reach more towards the surface, the amount of sediment or rock or earth material over them decreases, right? So that pressure on them is removed. And as they don't have that pressure that's keeping them down any longer, these rocks will then expand, right? Because they're not being compressed and squeezed down anymore. They'll kind of relax and they'll expand open. As these rocks expand, they'll typically start to fracture, which will break these rocks apart. Which brings us to something called frost wedging or the freeze and thaw cycle, which is another component of physical weathering. So when water seeps into cracks within a rock, um, right, it will fill that crack. If it's in an area where temperatures get cold, that water will eventually freeze. And because we know that water in its liquid form is more dense than ice in its solid form, that means that water expands when it freezes, right? So our water, as it freezes, will expand about 9% of its volume, which will then wedge apart that rock and crack it open. With repeat, many of these freeze and thaw cycles, the rock will be broken apart into pieces. So we will grow those fractures and can just break that rock completely apart. Okay, another component or another process of physical erosion is caused by glaciers. So glaciers, as they're moving across the earth, right? Because glaciers and ice sheets, which we will talk about in our next section, the cryosphere, they are formed on top of land surface, not sea ice that's formed in the ocean. Glaciers are formed on land and they move, right? So as the glacier is moving, all this ice is it's sliding over hard bedrock. It is grinding up that rock and scraping it away. So at these high latitudes where glaciers form, it's grinding these things away. On the right, I have a picture of a U-shaped valley, which is a glacial erosional landform. So here in this U shape was created because a glacier used to be here. The glacier is no longer here, but we can see these remnants and this characteristic clean U shape where all of that material has been scraped away over thousands and thousands of years by that ice moving. And that will typically create these very fine sediments called sills, which is would create, say, a mudstone, for example. Okay, so there are also biophysical erosion. So plant roots can penetrate fractures in a rock, and then they'll actually wedge that rock apart because plant roots are stronger than you would ever think that they are. They are very strong. On the right here is a photo of some of these very large trees that are growing in this rock fracture in a rock. And then you can see all these arrows pointing to these areas of root pry. So where these roots are physically wedging this rock apart. Okay, and finally we have chemical dissolution. So the chemical dissolution of minerals occurs whenever rock or minerals are exposed to rainwater and acidic soil. This will produce dissolved minerals and insoluble clays that form in those soils that is left behind. On the right, here's a photo or a diagram of this process. So first in this diagram, we have in this darker brown some very hard rocks, and then we have between it regolith. So as that those have been cemented together. So hard rock with regolith, that is softer form of that unconsolidated rock. If that is exposed to rainwater, that is say acidic, this acidic regolith will react. Um, this acidic rainwater with the carbonic acid will react with this regolith and it will chemically break it down. So it'll have dissolved particles within that rain be carried away from that rock, removing that substrate, and then leaving us with our weathered regolith, our very like tiny rocks on its own, with all these cracks that again can then be coupled with, say, this freeze and thaw cycle, wedging these open further and just keep on breaking it all apart. So those are all of our forms of weathering. Okay, next we have erosion. So erosion is defined as the transport of the products of weathering into basins where then sediments can accumulate to create those sedimentary rocks. So crustal materials and clays are transported by the wind, landslides, streams into these sites of deposition. So on the right, I have some diagrams here showing you some types of erosion. So at the top, we have rivers carving into a valley, right? Physically all that water, removing those sediments, carrying it downstream and removing it. Um, Here you can think of something like the Grand Canyon or those slot canyons that I showed. Those are all by rivers carrying and carving away that material. Next, we have wind blowing topsoil away. We also have waves cutting back cliffs near a shore where all that wave action is causing all that erosion. Okay, at the bottom we have glacier moving rocks such as boulders that it can deposit them, but it will also entrain them within the glacier itself, deposit them elsewhere, and this also grinding up that soil itself on the bottom. And then we have landslides where we are just dislodging that material downslope. Importantly, all the landscapes that we know of, right, all landscapes are created by this process of erosion, where we are taking all of the rock and material that is at these higher elevations, transporting it to lower elevations into valleys, as all of the erodible material is removed, leaving behind our beautiful landscapes that we have around the world. So, right, so we have our weathering that's removing materials and our erosion that's removing materials. Now, the last part of this is sediment accumulation. So sediment accumulation, it depends on the rate of supply of those materials and the amount of space that's available for deposition. So burial will, for example, sediments deposited in the deep ocean have a lot of space for these very, very thick sediments to accumulate. As you accumulate more sediments, you reduce the amount of space you have unless you're kind of moving that plate boundary or that interface vertically. Um, that can result in some sediments kind of reaching really close to the surface or creating shallow waters. So as sediments accumulate, maybe the seafloor rises, and then you're decreasing the amount of space you have. So there's also the burial of different components, right? So as you keep on accumulating sediments on top of one another, you start to bury the old ones. So this will cause material to compact because of the increasing weight of those overlying sediments will kind of squeeze and crush it shut. Think of just keep on piling books on yourself. You will start to keep on feeling that way as people keep putting books on you. right? And you'll feel more pressure. So if the weight of the overlying material is heavier enough, um, it can cause something such it can cause the fluids trapped between these sediment grains to be expelled. So this is shown on the picture on the right hand side. So here we have our sediments accumulating in this basin here. The basin is shown in this dark gray. So sediments that are closer to the surface have a porosity. So there is space between each of these different sediment grains. As the sediments are further compact, like we have in the middle, um, all of these components or all of the different sediments are squeezed together, where all of that porosity and any fluids that are trapped there, liquids, are expelled from that substrate. So these sediments or fluids trapped between the sediment grains will be expelled. Importantly, as we keep burying any of these sediments, we will also be increasing our temperatures and our pressures with depth here. So eventually, we'll bury all of these different sediments enough that not only have we expelled all of the fluids, but all the small voids between these sediment grains will be filled with mineral cements that are precipitated from subsurface fluids that are then deposited and cemented into all of those grains. So the cementation creates the hardening of those sediments. And then after all that, once you have that cementation, you have then cemented your sediments together and they are now lithified into sedimentary rock. So a sedimentary rock is now born. So, once formed, these sedimentary rocks can then be uplifted again. Um, so during tectonic plate collisions that create topography, such as mountain ranges that are then destroyed by erosion. So really uplift or mountains and mountain ranges in general are created as by the competition between the rate of uplift and the rate of erosion. So erosion promotes the recycling of sedimentary rocks before metamorphism or melting occurs. So we can create them and then just start to erode them right away without them transforming into anything else. Weathering and erosion will begin once a sedimentary rock becomes exposed at the surface. So again, mountains are the competition between uplift and erosion. Um, then we can look at some different mountain ranges. So we have newer mountain ranges such as the Himalayas, which are currently still going under this rapid uplift process to create the Mount Everest, the largest mountain in the world, the highest elevations. So in that instance, the rate of uplift is faster than the rate of erosion because it's still very tall. That is in stark contrast to some of our older mountain ranges, such as the Appalachian Range, where they're so old that uplift has very much slowed since then. So they're not really uplifting anymore. But of course, they're still eroding. So now they are, not the steep mountains of the Rocky, like the steep range of the Rocky Mountains. That's not the main ski destination in the country. Instead, great hiking destination. And people are living there and everything, and there's lots of trees. But they're just much more eroded. So this competition also changes through a mountain range's lifetime. Here on the right hand side, I have a mountain range. I do not know where this photo is from, but just by how rocky and how cliffy it looks, like lots of cliffs up there, I would then estimate this is a younger mountain belt because they are not nice and round and eroded if it were very, very old. Okay, so then you can also have your metamorphism and your melting in your rock cycle. So if a sedimentary or really an igneous rock either is buried, and then if it is subjected to these high temperatures and pressures of the Earth's interior, they will start to metamorphose. So if the rocks get hot without melting, they are called a metamorphic rock. And this occurs deep within sedimentary basins. So on the right, I have a figure here with our surface, and then we have some layers of sediments that have built. As we increase our depth, we are increasing our pressures and our temperatures exerted by the rock. So in this layer in gray here, we have our metamorphic rock where it has not melted yet, but it is exposed to all the heat of the adjacent molten rock. Um, if this is then uplifted from this point without melting completely, we will have our metamorphic rock that we'll see on the Earth surface. And here is a picture of just some examples of our metamorphic rocks. Okay, so now that we discussed all this, this is really closing the loop of our rock cycle. So, as a recap, or as putting this all this information into a diagram, we can see basically kind of a loop kind of structure, which is our rock cycle. So if we remember, right, our rocks are born and they die as magma or molten rock, and their life cycle or their cycle is all the different things that they can do in between those two times. And of course, we have a lot of rocks that are old, some that are young. So on the Earth's surface, we have rocks in every single stage of the cycle, really. Okay, so in the left-hand quarter, if we start from the birth of the rocks, we have our magma from the molten crust in the mantle, rises to the surface through a volcano here, and it is then extruded on the surface to create our basalt, right? Creating our igneous rocks. Once we have an igneous rock, they can then be weathered and eroded at the Earth's surface, creating or becoming sediments, right? Broken apart into these little pieces, which are called sediments. These sediments are then transported by erosional processes, all different erosional processes, into basins, lower elevations, where they are then deposited and then they are then lithified in these sedimentary basins to become sedimentary rocks. Okay, sedimentary rocks then have a few paths in which they can go, right? So now we're on the right-hand side of the first figure. And if we're looking at our other rock cycle diagram from the textbook, we're now at the bottom of this cycle here, right? So if we have a sedimentary rock, there are two things that can happen. One, it can get eroded or uplifted by our plate tectonic motion really quickly. So it can just go from sedimentary, doesn't experience any high temperature or pressure, really, only that lithification. So it kind of stays the same there. And if it goes back up to the surface, then once it reaches it, it will then start to be weathered and eroded again, transported across the Earth's surface, deposited at some point into a basin, creating sedimentation, compacted, cemented again, and then it will become a sedimentary rock again. So it can travel around in that loop a lot, right? Alternatively, it can get buried deeper and experience burial, where our temperatures and our pressures are very high. Temperatures can exceed 200 degrees Celsius, and our pressures can reach that of several, maybe tens or 100 times the pressures that we experience in our atmosphere, hundreds of times atmospheric pressures. So if we do that and we bury them, or expose them to high temperatures and pressures, and then we start to deform them in some way, they will become a metamorphic rock, where all this high temperature and pressure will change those chemical compositions. That metamorphic rock can either get uplifted to the surface again, where it is then eroded, transported, deposited, reaches a basin where it is cemented, compacted into a new sedimentary rock with all those sediments now of that metamorphic rock, or it can keep getting buried, melted completely, then it is magma again, and the next time it reaches the surface, it will become an igneous rock anew. Um, so that is our rock cycle. So this is the end of our rock cycle. I am going to post a three questions that I would have asked if we were in lecture right now, to Blackboard right underneath this video. They will be available for you to do for a week for the same amount of extra credit, um, points as a normal in-class polling question. I will make that due date by the end of class on Friday of this week, which would be, let me look it up. Okay, it will be due on Friday, March 28th at midnight. So it will be locked after that point. So if you answer them, if you get it right or wrong, it doesn't matter. Hopefully you get it right because they're not very difficult. And we just talked about this, but if you just do them for completion credit, you will get 3/10 of a point added onto your grade, just like any polling question. Okay, I will see everyone in class on Wednesday.